Far beyond the familiar constellations that light up our night sky, hidden within the vast expanse of space, lies a cosmic enigma so perplexing that even the brightest minds in astrophysics struggle to explain it. Welcome to the Leo Cluster, a gathering of galaxies so massive, so utterly bizarre, that it challenges everything we think we know about the universe. Picture this: hundreds of galaxies, each with billions of stars, swirling together in a dance that defies the laws of gravity as we understand them. But here's the unsettling truth: something invisible, something we can't yet detect, is pulling the strings. And today, we're about to uncover 25 of its deepest, most unsettling secrets. What if I told you that entire galaxies within the Leo cluster are moving too fast, as if propelled by some unseen force? Or that pockets of space here emit bizarre, unexplained radio waves with no discernible source? This isn't science fiction, it's real, and it's happening right now, millions of light years away. Scientists have spent decades staring into the heart of this cosmic anomaly, and yet the more they learn, the more questions arise. Dark matter, rogue black holes, even whispers of dimensions beyond our own, all of it tangled together in a mystery that rewrites the rules of physics. So why does this matter to you? Because the Leo cluster isn't just some distant spectacle, it's a window into the very fabric of reality. Every unexplained phenomenon we're about to explore isn't just a curiosity. It's a clue, a piece of a puzzle that could redefine our place in the cosmos. And as we dive into these 25 mysteries, from ghostly gravitational anomalies to galaxies that shouldn't exist, you'll start to see the universe in a way you never have before. Buckle up, this journey isn't just about what we know, it's about what we don't, and the thrilling, humbling possibility that the answers might be stranger than anything we've ever imagined. Deep within the Leo cluster, astronomers once observed a brilliant quasar shining with the light of 1 trillion suns until one day, it simply blinked out of existence. This wasn't a slow dimming or a gradual fade. It vanished as if someone flipped a cosmic switch, leaving behind no trace, no afterglow, just an eerie silence in the data. Quasars, the brightest objects in the universe, are powered by supermassive black holes devouring entire stars. They don't just disappear, or at least that's what we thought. So what could have snuffed out such a colossal source of energy? One leading theory suggests the quasar's black hole might have collided with another, their merger disrupting the violent feeding frenzy that makes quasars shine. But here's the catch: black hole mergers should release gravitational waves, ripples in spacetime that we've detected before, yet no such signal was recorded. Another possibility, a thick shroud of cosmic dust drifting across our line of sight, could have blocked the quasar's light entirely. But dust clouds don't move fast enough to explain how abruptly the light vanished. Then there's the wild card, something we haven't even imagined yet. The Leo cluster is a playground for the unexplained, where conventional physics often hits a wall. Could this quasar's disappearance be a sign of exotic matter, or even a phenomenon from higher dimensions leaking into our reality? Whatever the answer, one thing is clear: our models of how quasars live and die are missing a critical piece. And until we find it, the universe is keeping this secret locked away in the darkness of the Leo cluster. There's a galaxy in the Leo cluster that shouldn't exist, at least not according to everything we know about how galaxies work. Scientists call it the Phantom Galaxy, and here's why it's keeping astronomers up at night. This cosmic oddball appears to have no dark matter whatsoever. That's like finding a car running without an engine, because dark matter is the invisible scaffolding that holds galaxies together. Without it, stars should fly apart, yet this galaxy spins calmly as if nothing's wrong. The discovery sent shockwaves through the astrophysics community because it challenges a fundamental rule: that dark matter outpaces normal matter 5 to 1 in every galaxy we've studied. When researchers first measured the phantom galaxy's rotation, they expected to see the telltale tug of dark matter's gravity. Instead, the stars moved exactly as predicted by visible matter alone, as if the dark matter had simply vanished. Some scientists argued it was a measurement error, while others wondered if we'd misunderstood galaxy formation entirely. One radical theory suggests the phantom galaxy might be a tidal dwarf, a galaxy born from the debris of two colliding giants, where dark matter got left behind like crumbs from a cosmic collision. Others propose that dark matter particles interact in ways we can't yet detect, making them invisible even to our most sensitive instruments, but the most unsettling possibility. That dark matter isn't uniform across the universe at all, that some regions, like this quiet corner of the Leo cluster, operate by entirely different rules. Whatever the truth, this ghostly galaxy forces us to confront an uncomfortable reality. The universe might be playing by a playbook we haven't even found yet. Stretching like an invisible bridge between galaxies in the Leo cluster, there's a structure so massive, so bizarrely influential, that it warps the very fabric of space around it. Scientists call it the gravity-defying filament, a thread of cosmic material spanning millions of light years, twisting spacetime in ways that defy every expectation. Here's what makes it so unsettling. The gravitational pull it exerts is far stronger than anything its visible matter can account for. It's as if there's an entire hidden dimension tugging on the universe's seams, and this filament is its fingerprint. When astronomers first mapped the filament, they expected its gravity to match the glow of hot gas and scattered stars within it. Instead, they found galaxies on either side being dragged toward the filament at speeds that shouldn't be possible. It's like watching marbles roll uphill without a slope, a violation of cosmic rules we thought were set in stone. Some researchers argue this could be the largest concentration of dark matter ever observed, a river of invisible particles weaving through the cluster. But even that explanation falls short. The filament's gravitational distortions are too extreme, too focused, as if something else, something beyond dark matter, is at work. One theory suggests the filament might be a cosmic wake, left behind by a supermassive black hole that shot through the cluster like a bullet, warping spacetime in its path. Another idea points to quantum fields we haven't yet detected, permeating the universe and leaving behind strange imprints, but the most mind-bending possibility: that this filament is a wrinkle in spacetime itself, a flaw in the universe's geometry where gravity behaves in ways we can't yet model. Every telescope trained on it raises more questions than answers, and until we crack this code, the gravity-defying filament remains one of the Leo cluster's most tantalizing mysteries, a reminder that even the laws of physics might have exceptions we've yet to discover. Buried in the static of deep space, two ghostly radio signals flicker in and out of existence, defying every attempt to pin them down. These twin radio ghosts of the Leo cluster aren't just mysterious, they're cosmic shape-shifters, mimicking known objects one moment and vanishing the next. Unlike pulsars, which pulse with metronomic precision, or active galactic nuclei that roar with steady energy, these phantoms appear without warning, broadcast for days or even weeks, then dissolve into silence as if they were never there. Take their bizarre frequency patterns, for instance. Typical radio sources like pulsars emit in clean, predictable bands, like a radio station tuned to one frequency. But the twin ghosts, their signals jump erratically across the spectrum, as if someone's twisting a dial at random. Even more perplexing, their brightness fluctuates by factors of 10 in mere hours, something no known celestial object should be capable of. And the violent hearts of galaxies can vary over months or years, but nothing this extreme, this fast. It's like comparing a candle's flicker to a strobe light in a thunderstorm. Then there's the spacing. These two sources are separated by nearly 300,000 light years, yet their outbursts occasionally sync up as if linked by some unseen thread. Coincidence, maybe, But when one flared to life in 2019, astronomers scrambled to train every telescope they had on the second, only to watch it awaken precisely 48 hours later. The odds of that happening by chance are astronomically low, pun intended. So what could they be? One radical hypothesis suggests orphaned magnetars, super-dense stellar corpses ejected from their home galaxies, spinning wildly through the void. But magnetars usually emit X-rays, not radio waves, and their bursts last seconds, not weeks. Another idea, colliding dark matter particles, annihilating in flashes we're only now detecting. But dark matter isn't supposed to interact with radio frequencies at all. The truth is, every explanation crumbles under scrutiny, leaving us with a haunting possibility. These twin radio ghosts might be our first glimpse of an entirely new class of cosmic object, one that operates by rules we haven't written yet. And until we solve their riddle, they'll keep whispering from the shadows of the Leo cluster, taunting us with signals we can't decode. In the heart of the Leo cluster, astronomers witnessed a stellar explosion so violent, so impossibly bright, that it forced us to rewrite the textbooks on how stars die. Dubbed the Impossible Supernova, this cataclysmic event outshone entire galaxies for months, burning with the intensity of 100 normal supernova combined. What made it truly bizarre wasn't just its brilliance, it was the fact that it refused to fade. Most supernova dim within weeks, but this one raged on like a cosmic bonfire, defying every known model of stellar destruction. At first, scientists assumed it was a pair instability supernova, a rare type of explosion that occurs in massive stars with cores so hot they spontaneously create matter and antimatter pairs. These runaway reactions should rip the star apart completely, leaving no remnant behind. But here's the problem: the energy signature was all wrong. Pair instability explosions are supposed to be one and done events, yet this supernova's light curve showed strange, rhythmic fluctuations, as if something inside was still feeding the fire. Then there's the location. The Leo cluster isn't known for birthing the kind of ultra-massive stars that produce pair instability explosions. Most of its galaxies are old and metal-rich, environments where stars rarely grow large enough to trigger such extreme detonations. So was this a cosmic fluke, or did we stumble upon an entirely new way for stars to self-destruct? One controversial theory suggests the supernova might have been triggered by a collision between two stellar remnants, perhaps a neutron star spiraling into a black hole, releasing energy in ways we've never seen. Others speculated could have been a magnetorotational supernova, where a dying star's magnetic field and rotation conspire to create an explosion unlike any other. But the most unsettling possibility, that we witnessed the death throes of a hypothetical quasi-star, a primordial monster from the early universe that shouldn't still exist today. Whatever the truth, the Impossible Supernova left behind more than just an afterglow. It left a gaping hole in our understanding of stellar physics. And until we find another like it, this brilliant anomaly will remain one of the Leo cluster's most enduring puzzles, a blazing reminder that the universe still holds secrets we can't yet fathom. Hidden in the Leo cluster's swirling tapestry of galaxies lies a cosmic paradox, a region so empty it's full of questions. Scientists call it the dark matter void, a pocket of space where the universe's most abundant ingredient seems to have gone missing. Picture a massive, invisible hand scooping out the glue that holds galaxies together, leaving behind a gravitational ghost town. This isn't just an absence, it's a rebellion against everything we thought we knew about how dark matter behaves. Normally, dark matter acts like cosmic scaffolding, its gravitational pull shaping the cluster's structure. Galaxies orbit faster, and light bends more sharply around concentrations of it. But here, the rules break down. Measurements show galaxies drifting lazily, as if the unseen force anchoring them simply evaporated. The void's gravitational footprint is a whisper compared to what it should be, like a fingerprint smudged beyond recognition. One theory suggests a violent past, perhaps a collision between two dark matter halos, scattering particles like billiard balls and leaving this barren patch. Another idea points to dark matter's hypothetical self-interactions, where particles might annihilate or repel each other in ways we've never observed. But here's the twist: computer simulations can't reproduce or avoid this extreme without breaking known physics. It's as if the universe played a prank, carving out a space where its own rules don't apply. The implications are staggering. If dark matter isn't uniformly distributed, our models of galaxy formation and even the fate of the cosmos might need rewriting. Could this void be a flaw in our theories or a clue to something deeper? Perhaps dark matter isn't a single substance but a family of particles, some of which behave in ways we've yet to imagine. Whatever the answer, this silent corner of the Leo cluster screams one thing loud and clear: the universe is still hiding its most fundamental secrets in plain sight. Amid the chaos of the Leo cluster's swirling galaxies, a tiny point of light blinks with eerie precision, like a cosmic metronome keeping time across the universe. This is no ordinary star or pulsar. It's a repeating fast radio burst, a pulse of energy so powerful it outshines entire galaxies for milliseconds, vanishing before our telescopes can fully grasp it. What makes this one extraordinary isn't just its existence, it's the uncanny regularity of its beats, arriving like clockwork every 137 days. No known natural phenomenon behaves with this level of consistency, and that's precisely why it's rattling the scientific community. At first glance, fast radio bursts, or FRB, seem like cosmic accidents, the universe's way of flicking a lighter in the dark. Most are one-off events, chaotic sparks from collisions or collapsing stars, but this Leo cluster repeater defies the pattern. Its signal isn't just repeating, it's predictable, cycling through active phases and silence with the precision of a machine. When astronomers first noticed the pattern, they checked and rechecked their data, assuming an error. But the bursts kept coming, each one a screaming flare of radio waves traveling billions of light years without losing their rhythm. So what's behind this celestial timer? The leading theory points to magnetars, neutron stars with magnetic fields so intense they could strip the electrons from atoms halfway across the galaxy. These super-dense stellar corpses occasionally glitch, releasing violent flares that might explain one-off FRBs. But for a repeating burst with such tight timing, the magnetar would need an external trigger, perhaps an orbiting companion star warping its magnetic field like a cosmic wrench. Even then, maintaining this level of precision over centuries stretches our understanding of stellar mechanics to the breaking point. Then there's the fringe hypothesis, the one that makes headlines but divides scientists' technosignatures. Could this be evidence of advanced extraterrestrial engineering? The idea isn't as far-fetched as it sounds. A civilization capable of harnessing stellar energy might use directed radio beams for communication or propulsion, creating pulses detectable across the cosmos. But here's the catch: nature rarely winks at us this deliberately. The signal's artificiality isn't proven, just uncomfortably coincidental. Most researchers dismiss the notion, arguing that invoking aliens is a last resort when natural explanations remain unexplored. Yet the mystery deepens when you examine the burst structure. Each pulse contains sub-millisecond spikes, finer than any natural process should allow, as if the source is chirping in a language we can't decode. Some astrophysicists compare it to a lighthouse beam sweeping past Earth, while others wonder if we're seeing the aftermath of exotic physics, black hole echoes, cosmic strings vibrating like plucked guitar wires, or even leaks from a higher dimensional space. The truth is, this repeating FRB isn't just a puzzle, it's a mirror. However we interpret it, as a magnetar's cry, a flaw in relativity, or something beyond our current science, it reflects back the limits of human knowledge. And until we catch it in the act with newer, sharper eyes, the Leo cluster's rhythmic enigma will keep pulsing, a silent question mark in the static between the stars. Gravity doesn't just pull, It bends, twists, and warps the very fabric of reality. And nowhere is this more unsettling than in the Leo cluster, where a cosmic funhouse mirror distorts distant starlight into something impossible, a broken, lopsided ring that shouldn't exist. Known as the warped Einstein ring, this bizarre optical illusion occurs when a massive foreground galaxy bends light from an object directly behind it, creating what should be a perfect circle of distorted glow. But here's the catch: this ring isn't perfect. It's jagged, uneven, stretched like taffy in some places and pinched in others, as if unseen hands are tugging at spacetime itself. Einstein's theory of general relativity predicts these rings with elegant precision. When everything aligns just right, the mass of the foreground galaxy, the distance of the background object, the smooth distribution of matter, the result should resemble a glowing halo, a so-called Einstein ring. But the Leo cluster's version looks more like a ring dropped on hot pavement, its symmetry shattered by forces we can't yet explain. The culprit, an invisible imbalance in the cluster's mass. Gravitational lensing acts like a cosmic scale, measuring how matter warps light. For the ring to distort this dramatically, something's tipping the scales, either vast clouds of dark matter clumped unevenly or rogue structures we haven't detected. Some researchers suggest the foreground galaxy might harbor a supermassive black hole dancing erratically through its core, its gravity creating chaotic ripples in the lensing effect. Others point to dark matter subhalos, invisible clumps orbiting the main galaxy like moons, each adding their own gravitational fingerprint to the distortion. But the most startling possibility, that our entire understanding of how mass clusters in galaxies might be flawed. Simulations can't replicate the rings warping without breaking known physics, hinting that dark matter, if it exists at all, might behave in ways far stranger than we've assumed. Perhaps it interacts with itself, forming dense knots that twist light unpredictably. Or maybe gravity itself works differently on these scales, bending not just to mass but to some hidden variable we've yet to uncover. Every flicker of this warped ring is a challenge, a cosmic riddle scrawled in bent starlight. And until we decipher it, the Leo cluster's distorted-looking glass will keep reflecting back a universe more mysterious, more defiant than we ever imagined. Deep in the Leo cluster, two supermassive black holes refuse to play by the rules. These aren't your typical galactic monsters, feeding steadily on stars and gas they flicker. Like cosmic light switches stuck between on and off, their brightness spikes and plummets unpredictably, sometimes vanishing entirely for months before roaring back to life. Astronomers call them the flickering duo, and their erratic behavior is rewriting what we thought we knew about how black holes feast. Take a typical active galactic nucleus, or AN, the bright, chaotic region around a feeding supermassive black hole. Most AGNs fluctuate, sure, but in predictable rhythms. Gas spirals into the black hole's disk, heats up, and glows fiercely before settling into a steady simmer. The flickering duo, their light curves look like a frantic heartbeat, with luminosity swings up to 100 times more extreme than anything models predicted. One moment they're among the brightest objects in the cluster, the next they're barely detectable. It's as if someone's turning their power supply on and off at random. So what's jamming the cosmic dimmer switch? One theory points to chaotic feeding. Most black holes snack on gas clouds that orbit in orderly, flattened disks. But simulations suggest these two might be gulping down shredded stars or turbulent gas clumps in erratic bursts, creating violent hiccups in their accretion flow. Imagine trying to drink a smoothie through a straw, except the straw keeps kinking, and the smoothie is laced with unpredictable chunks. That's the kind of messy feast these black holes seem to be enduring. Then there's the wild card, magnetic strangulation. Black holes generate immense magnetic fields that can sometimes choke off their own food supply, like a cosmic version of pinching a hose. If these fields twist into unstable knots, they might sporadically block infalling matter, starving the black hole until the pressure breaks the dam. But here's the catch: no known magnetic configuration explains the duo's specific flicker patterns. Their shutdowns are too sudden, too complete, as if something's yanking the dinner plate away entirely. The most tantalizing possibility: we're witnessing a cosmic duel. Some researchers speculate these black holes could be locked in a gravitational tango, their mutual orbits tossing gas streams into chaos. As they swing close, tidal forces might strip each other's accretion disks, triggering violent feeding frenzies followed by abrupt droughts. It's a delicate dance, one that could eventually end in a collision, shaking the fabric of spacetime with gravitational waves. But for now, their flickering remains a cryptic signal, a pair of cosmic moths fluttering around a flame we can't yet see. Whatever the cause, the flickering duo forces us to confront a humbling truth. Even the most voracious objects in the universe have moods we don't yet understand. And until we crack their code, these black holes will keep blinking at us from the dark, a silent challenge to our models of how chaos shapes the cosmos. Stretching across the Leo cluster like a flaw in the cosmos, there's an anomaly so strange, so delicately precise, that it might be a relic from the universe's first moments. Scientists call it the cosmic string candidate, a thread of pure spacetime tension, thinner than a proton yet dense enough to warp light from galaxies behind it. If confirmed, this isn't just another oddity, it's a fossil from the Big Bang itself, a crack in reality's foundation left over from when the universe was hotter than a trillion suns. Cosmic strings were first proposed as mathematical quirks in quantum field theory, hypothetical one-dimensional defects in spacetime, formed when the infant universe underwent phase transitions like ice cracking as it freezes. But unlike ice, these cracks would be indestructible, carrying unimaginable density in their razor-thin cores. A single centimeter of cosmic string could outweigh Mount Everest. The Leo cluster's candidate fits the profile eerily well, a perfectly straight gravitational lensing effect, bending distant starlight along its length without any visible mass to explain it. No black hole, no dark matter cloud, just empty space twisting light as if under invisible wires. What makes this potential string revolutionary isn't just its existence, but what it could reveal. According to some theories, cosmic strings should vibrate like guitar strings, emitting gravitational waves at frequencies we've never detected. Finding one could be the key to unifying quantum mechanics and general relativity, a bridge between the infinitely small and the cosmically vast. Even more tantalizing, their vibrations might create kinks or loops that collapse into primordial black holes, seeding the universe's structure before galaxies even formed. Yet skepticism lingers. Alternative explanations suggest the lensing could come from an impossibly aligned chain of dark matter subhalos, or a chance superposition of unrelated gravitational fields. But the candidate's razor-straight geometry defies these odds. Supercomputer simulations show such perfect alignment occurring naturally less than once in a billion universes. If this is a cosmic string, its implications ripple far beyond Leo. It could mean our universe is laced with similar filaments, a hidden web of spacetime defects shaping everything from galaxy formation to the spread of dark energy. Or perhaps this string is alone, a solitary remnant of a more violent cosmic infancy than we'd imagined. Until we develop telescopes sensitive enough to measure its hypothetical vibrations or hunt for telltale distortions in the cosmic microwave background, the string's truth remains suspended, like the anomaly itself between discovery and legend. Most stars move through galaxies with stately grace, obeying the universal dance of gravity, but not this one. In the Leo cluster, astronomers have spotted a runaway star racing through space at nearly 3 million miles per hour, so fast it's tearing free of the cluster's gravitational grip entirely. They call it the unbound hypervelocity star, and its existence defies every model of stellar motion we've ever built. This isn't just a star kicked out of its neighborhood, it's a cosmic bullet fired from an invisible gun. Normally, stars reach such extreme speeds through dramatic encounters like a close brush with a supermassive black hole, which can slingshot them outward like stones from a catapult. But here's the catch. The Leo cluster's central galaxies show no signs of harboring black holes massive enough to launch this stellar fugitive. Even if they did, the star's trajectory doesn't point back to any plausible origin point. It's as if it was hurled into motion by something we can't see. That missing something has scientists scrambling. One leading theory suggests a rogue intermediate mass black hole lurking undetected in the cluster's outskirts might have flung the star away during a chance encounter. These elusive mid-sized black holes are thought to exist but have proven notoriously hard to spot. If one is hiding in the Leo cluster, its gravitational kick could explain the star's insane velocity. But there's a problem. Even that scenario requires nearly perfect alignment to achieve this kind of speed, making it astronomically unlikely. Then there's the dark matter angle. Some researchers propose that clumps of dark matter, drifting like invisible icebergs through the cluster, could have gravitationally bumped the star in just the right way to send it careening. These interactions would leave no visible trace, only the star's frantic motion as evidence. It's a tantalizing idea, but dark matter, by definition, doesn't interact with stars in ways we can easily model. Perhaps the most mind-bending possibility is that this star didn't originate in the Leo cluster at all. Hypervelocity stars are known to escape other galaxies, sometimes crossing intergalactic space before being captured by new gravitational fields. Could this be an intruder from another cluster entirely, a cosmic hitchhiker that slipped into Leo's grasp? Spectral analysis of its light hints at an unusual chemical composition, suggesting it might have formed in a very different environment. Yet even that theory doesn't fully explain its speed. Whatever launched this star didn't just nudge it, it unleashed a force comparable to a supernova explosion, but without the accompanying fireworks. Until we find more of these stellar speedsters or pinpoint their launch mechanisms, the unbound hypervelocity star will remain a blazing question mark, streaking through the cosmos as a reminder that even the most familiar objects can defy the rules when we least expect it. Floating like a phantom in the depths of the Leo cluster, there's a cosmic oddity that emits more X-rays than some entire galaxies, yet no one can figure out what's powering it. This is the X-ray mystery cloud, a sprawling, faint glow of high-energy particles stretching across thousands of light-years. Unlike the brilliant cores of active galaxies or the concentrated fury of black holes, this cloud is diffuse, almost lazy in its radiation, as if the universe left a cosmic stove burning without a flame. At first glance, it resembles the aftermath of a galactic car crash, the kind of debris field you'd expect when two galaxies collide, their gas heated to millions of degrees by the violence of the encounter. But here's the twist. There's no wreckage nearby, no mangled spiral arms or distorted star clusters to suggest a recent collision. The cloud hangs in isolation, a glowing enigma adrift in the cluster's sea of galaxies. Then there's the energy problem. X-rays this intense usually come from one of two sources: superheated gas funneled into a black hole's maw, or the shock waves of exploding stars. But the mystery cloud shows no signs of either. Its temperature is too uniform, lacking the turbulent fingerprints of black hole feeding frenzies. And while supernova could, in theory, heat gas to X-ray, emitting temperatures, you'd need thousands of them exploding in sync, a stellar fireworks show on a scale never observed. One radical hypothesis suggests this might be the ghost of a failed galaxy, a clump of dark matter that never quite gathered enough gas to ignite star formation. Over billions of years, trace amounts of hydrogen could have slowly accumulated, heated by the faint gravitational pull of the unseen dark matter, eventually reaching temperatures hot enough to glow in X-rays. It's a stretch, but not impossible. Another idea: the cloud could be the echo of a long-forgotten cataclysm. Imagine a supermassive black hole ejected from its host galaxy eons ago, careening through the cluster like a runaway cannonball. As it plowed through intergalactic gas, it might have left behind a trail of shocked, X-ray emitting material, a cosmic contrail fading into the darkness. The challenge: no such rogue black hole has been found nearby. And then there's the wildest possibility of all, that we're seeing a previously unknown state of matter. Some theories predict exotic particles or quantum phenomena that could generate diffuse X-rays without conventional energy sources. If true, this cloud might be our first glimpse of physics operating on scales or in ways we've never imagined. For now, the X-ray mystery cloud remains just that, a mystery. Every explanation has holes, every theory a loose thread, but that's what makes it so compelling. In a universe where we've mapped the cosmic microwave background and photographed black holes, this faint, glowing enigma reminds us that some of the cosmos' most profound secrets are still hiding in plain sight, waiting for us to ask the right questions. Deep in the Leo cluster, cosmic rays, those high-energy particles racing through space at nearly light speed, suddenly slam into an invisible wall. It's not a black hole's event horizon or a dense nebula blocking their path. This is something far stranger, a boundary where the universe itself seems to change its rules. One moment, detectors pick up the usual chaotic spray of cosmic rays. The next, they drop to near silence, as if someone erected a cosmic keep-out sign. Scientists call it the invisible barrier, and it's forcing us to question whether we've overlooked a fundamental force shaping the fabric of reality. Cosmic rays are the universe's bullets fired from supernova, active galaxies, and other violent events. They should streak through galaxy clusters unimpeded, their path slightly bent by magnetic fields but never abruptly halted. Yet here, in this quiet corner of the Leo cluster, they hit an edge sharper than any theoretical model predicts. It's like watching ocean waves crash against an unseen reef, a disruption that defies conventional physics. One compelling explanation ties into quantum field theory's most speculative ideas: domain walls. Picture the early universe cooling from its fiery birth, like molten metal solidifying into distinct crystals. Where these crystals meet, defects could form one-dimensional boundaries separating regions where quantum fields settled into different configurations. These domain walls would be unimaginably thin yet dense enough to stop particles cold, acting as cosmic force fields. If one slices through the Leo cluster, it might explain the sudden drop-off in cosmic rays. But there's a catch: domain walls, if they exist, should be ludicrously massive, warping spacetime so dramatically that we'd detect their gravity. The Leo cluster's barrier shows no such distortion, leaving researchers scrambling for alternatives. Could this be a shadow of dark matter's hidden structure? Some models suggest dark matter might clump into vast, sheet-like formations, their gravity too diffuse to notice, but their particle interactions just potent enough to deflect cosmic rays. Or perhaps the answer lies in magnetism. Galaxy clusters are threaded with magnetic fields, usually too weak to halt high-energy particles. But what if turbulence in the Leo cluster amplified these fields locally, creating a magnetic mirror that bounces cosmic rays away? The challenge is scale. Generating a field this strong would require energy equivalent to 1,000 supernova pumping into the same region, a coincidence that beggars belief. Then there's the outlier possibility that we're seeing evidence of a universe beyond our own. Some multiverse theories suggest boundaries between parallel realities could leave faint imprints on spacetime, like seams in a vast cosmic quilt. These edges might interact weakly with matter, stopping certain particles while letting others pass. It's a fringe idea, but the Leo cluster's barrier fits the profile eerily well, a place where the rules change without explanation. Whatever the truth, this invisible barrier isn't just a curiosity. It's a challenge to our understanding of cosmic geography. Most maps of the universe chart galaxies and voids, but they ignore the possibility of unseen structures lurking between them. If domains, dark matter sheets, or even multiverse boundaries are real, they could rewrite how we see everything from particle physics to the large-scale universe. Until we pierce this mystery, the Leo cluster's silent wall remains a humbling reminder. The cosmos might be gated in ways we're only beginning to imagine. Among the countless galaxies swirling through the Leo cluster, two stand out for their eerie, almost choreographed dance. Separated by over 500,000 light-years, far enough that light from one would take 500,000 years to reach the other, these galaxies spin in flawless unison, their spiral arms turning like synchronized clockwork. No visible threads of gas or stars link them, no tidal forces explain their mirrored motions. It's as if they're connected by invisible strings, whispering secrets across the void. Astronomers call them the synchronized galaxies, and their coordinated spin defies every conventional model of galactic behavior. Galaxies aren't supposed to move this way. Like cars on a highway, they follow their own paths, influenced by local gravity but rarely matching speeds with distant neighbors. Even in dense clusters where galaxies jostle like commuters in a crowd, such precise synchronization is unheard of. Normally, interactions this exact require proximity close enough for gravity to lock orbits, like the Moon's face forever turned toward Earth. Yet these two show no signs of ever having collided or brushed past each other. Their stars are pristine, their shapes undisturbed, as if they've always danced just out of reach. So what's conducting their cosmic waltz? One theory points to dark matter filaments, invisible rivers of the universe's most mysterious substance, flowing between galaxies like subterranean currents. If these filaments are dense enough, their gravity might subtly tether the galaxies, orchestrating their rotations like puppets on shared strings. Simulations show such structures could exist, woven through the cosmos in a vast, unseen web. But there's a catch. No current telescope can directly detect these hypothetical filaments, leaving the idea lingering in the realm of speculation. Another possibility digs deeper into quantum weirdness, primordial entanglement. In the universe's earliest moments, before space had fully stretched to its current scale, these galaxies might have been close enough for their quantum states to intertwine. As expansion pulled them apart, that connection could have persisted, linking their motions across cosmic distances. It's a radical idea, one that treats entire galaxies like subatomic particles, forever paired no matter how far apart they drift. While mainstream physics balks at scaling quantum effects to galactic proportions, some theorists argue the math doesn't rule it out. After all, if entanglement can bind electrons across labs on Earth, why not galaxies forged from the same fiery instant of creation? Then there's the wild card, a third, unseen player. Could a supermassive black hole, ejected from one galaxy long ago, now lurk between them, its gravity subtly synchronizing their spins? Or perhaps a hidden dwarf galaxy, too dim for our telescopes, acts as a gravitational intermediary, its influence choreographing the dance from the shadows. The truth is, the synchronized galaxies don't just challenge our understanding of how galaxies move, they force us to reconsider what connection even means in an expanding universe. Are we seeing the handiwork of dark matter, a quantum relic, or something entirely new? Every observation tightens the mystery, leaving astronomers staring at these mirrored spirals with equal parts awe and frustration. Until we crack their code, they'll keep spinning in perfect, silent harmony, a cosmic riddle written in starlight. At the edge of the Leo cluster, a quasar pulses with light that doesn't just flicker, it stutters, as if time itself is splintering around it. This is the time-dilated quasar, an active galactic nucleus whose emissions don't just dim and brighten like ordinary quasars. Its light stretches and compresses in bizarre, unpredictable lags, sometimes appearing to slow to a crawl before snapping back to normal speed. It's as if someone keeps twisting the dial on a cosmic DVR, warping reality's playback in ways that defy both relativity and common sense, the strangest part. These delays aren't random. They follow a pattern like a glitching heartbeat where every third pulse arrives late. Normally, quasars vary their brightness due to chaotic feeding gas clumps swirling into the central black hole at irregular intervals. But time dilation, that's supposed to be the domain of extreme gravity, like near a black hole's event horizon. Except this quasar's supermassive black hole, while enormous, isn't nearly massive enough to explain the effect. Its gravitational pull shouldn't be warping time to this degree, not unless our math is missing something fundamental. One theory dives deep into relativity's playbook. If the quasar's accretion disk were tilted at a precise angle, spinning at near light speeds, its outer edges might experience measurable time dilation from our vantage point. Imagine a carousel where the outermost horses move so fast, their clocks tick slower than those at the center. Except here, the carousel is a disk of superheated plasma larger than our solar system. But even that elegant solution falters when confronted with the data. The delays don't align with the predicted relativistic effects. They're too sharp, too abrupt, like a film reel skipping frames rather than smoothly slowing down. Then there's the spacetime ripple hypothesis. Some researchers suggest these anomalies could be evidence of gravitational waves from unseen cosmic events, colliding neutron stars or even primordial black holes passing through the quasar's light path like stones disturbing a pond. As these waves stretch and compress spacetime, they'd subtly alter the arrival time of the light waves, creating the illusion of intermittent slowdowns. The problem: current gravitational wave detectors haven't picked up any corresponding signals. Either the waves are too faint or their sources are beyond our observational reach. But the most unsettling possibility, that we're witnessing a flaw in spacetime itself. Quantum gravity theories predict that on the tiniest scales, the fabric of reality might be foamy and unstable, full of microscopic fluctuations that could occasionally bubble up to macroscopic effects. If true, the time-dilated quasar might be our first glimpse of this quantum foam in action, a place where the universe's underlying structure briefly frays, letting us peer behind the curtain of smooth, continuous spacetime we take for granted. Every flicker of this quasar is a challenge to physics as we know it. Whether it's revealing hidden dimensions, exposing gaps in relativity, or hinting at entirely new cosmic mechanics, one thing is certain: time in the Leo cluster doesn't always play by the rules. And until we crack this code, the universe will keep taunting us with these tantalizing hiccups in reality's rhythm. In the heart of the Leo cluster, there's a celestial paradox that's turning astrophysics on its head. A place where the universe's two most fundamental ingredients, galaxies and dark matter, seem to be playing a cosmic game of hide and seek. Scientists call it the anti-correlation zone, a region where the densest clumps of galaxies mysteriously avoid the densest patches of dark matter. It's like opening a freezer and finding the coldest spots empty of ice while warm corners are packed with it. This isn't just a curiosity, it's a direct challenge to our understanding of how gravity binds the cosmos together. Galaxies and dark matter are supposed to be inseparable partners. Dark matter's gravitational pull draws in gas and dust, creating the scaffolding for galaxies to form. Where one is abundant, the other should follow. Yet in this baffling zone, the rules reverse. Telescopes mapping the cluster's mass using techniques like gravitational lensing reveal dark matter pooling in areas where galaxies are sparse, while galaxy-rich neighborhoods sit atop near empty voids of invisible matter. It's as if the universe's glue has decided to work in reverse. So what's tearing this cosmic partnership apart? One radical explanation comes from modified gravity theories, like modified Newtonian dynamics. These frameworks propose that gravity behaves differently on vast scales, eliminating the need for dark matter altogether. If true, the anti-correlation zone might be a place where these alternative laws manifest most starkly, creating apparent gaps in mass where conventional models expect dark matter to lurk. But there's a problem. struggles to explain other observed phenomena in the Leo cluster, like the warped Einstein ring, leaving scientists hesitant to abandon dark matter entirely. Then there's the dark sector hypothesis, the idea that dark matter isn't a single, passive substance but a complex ecosystem of particles with their own interactions. Perhaps invisible forces between dark matter particles push them away from galaxies, like oil separating from water. Some models even suggest dark photons or other exotic carriers could mediate repulsive forces within the dark sector, creating these eerie anti-correlations. If proven, it would mean dark matter isn't just a backdrop to the universe's story, it's an active player with its own hidden physics. But the most tantalizing clue lies in the zone's location. It's not isolated. The anti-correlation zone overlaps with areas of unexplained radio emissions and gravitational anomalies, as if the cluster's strangest phenomena are conspiring in the same neighborhoods. Could this be a sign of something deeper, a fundamental misunderstanding of how mass and gravity intertwine? Every observation tightens the knot, leaving astronomers with a humbling realization. The universe's blueprint might have pages we haven't even glimpsed yet. And until we decipher this cosmic contradiction, the anti-correlation zone will stand as a silent rebellion against the rules we thought governed the heavens. Drifting through the emptiness between galaxies in the Leo cluster, there's a cosmic orphan, a glittering ball of stars so massive, so ancient, it could be the corpse of a galaxy long dead. Meet the orphan globular cluster, a celestial anomaly packing hundreds of thousands of stars into a tight sphere, yet floating utterly alone with no galactic parent to call home. This isn't just unusual, it's practically unheard of. Globular clusters are supposed to orbit galaxies like bees around a hive, bound by gravity's unbreakable chains. But this one, it's a rebel untethered, as if the universe itself forgot to assign it a place in the cosmic hierarchy. At first glance, the cluster looks like any other, a dense, spherical swarm of stars, their combined light a faint smudge against the dark. But here's the twist. When astronomers traced its motion, they found it wasn't circling any galaxy in the cluster. It's adrift, moving with the slow, aimless grace of a ship without a port. The leading theory, this might be all that remains of a dwarf galaxy torn apart eons ago. Its stars stripped away by the Leo cluster's immense gravity until only this resilient core survived. Like a fossilized bone in a cosmic graveyard, the cluster could be a relic of galactic cannibalism, a silent witness to the violent mergers that shaped the universe. But there's a problem with that story. The stars in this globular cluster are too old, even by the standards of such ancient structures. Their chemical composition hints at formation in the universe's first billion years, a time when galaxies were just beginning to coalesce. If it's the remnant of a devoured dwarf galaxy, why does it look older than the galaxies around it? One provocative idea flips the script entirely. Perhaps this cluster never had a host. Some models suggest the earliest globulars could have formed directly from primordial gas clouds, collapsing into starry knots before galaxies even existed. That would make this orphan not a galactic cast-off, but a lone survivor from the universe's infancy, a cosmic hermit that refused to join the dance of galaxies. Then there's the wildcard scenario, dark matter. If the cluster once belonged to a galaxy rich in dark matter, its unseen halo might have acted like an anchor, keeping the globular bound long after visible stars were ripped away. Over billions of years, as the dark matter dissipated or was stripped by tidal forces, the cluster could have been cut loose, set adrift like a boat slipping its moorings. The catch: no one's ever detected dark matter clinging to a globular cluster before. If this theory's right, it would mean these starry spheres are far more complex than we ever imagined. Whatever its origins, the orphan globular cluster forces us to confront a humbling truth. The universe is still writing its rulebook, whether it's a galactic ghost, a primordial fugitive, or something stranger still. This lonely star city reminds us that even the most familiar objects can defy expectations when we look closely enough. And until we solve its riddle, it will keep drifting through the void, a silent question mark written in starlight. Deep in the silent expanse of the Leo cluster, two bursts of gamma radiation echo each other with eerie precision, like cosmic twins separated by millions of light years, yet somehow moving in perfect, synchronized opposition. These are the ghostly gamma-ray pairs, mysterious sources of the universe's most energetic light, flaring in tandem across the void. What makes them extraordinary isn't just their intensity, it's their mirrored timing, as if an invisible thread connects them across impossible distances. Gamma rays typically come from violent, one-off events colliding neutron stars, supernova, or black holes devouring matter. They don't usually coordinate. But these two sources defy the pattern, their emissions flaring in lockstep, then fading together like lights flickering under the same switch, the strangest part. They're nowhere near each other. One lies on the cluster's eastern fringe, the other anchored to a galaxy group in the west. By all known physics, they shouldn't even be aware of each other's existence. So what's linking them? One tantalizing theory points to annihilation events, perhaps clouds of dark matter particles, colliding and obliterating each other in matched pockets of the cluster. If dark matter is its own antimatter counterpart, as some theories suggest, these mutual destructions could unleash paired gamma-ray bursts, visible only when the annihilation fronts align just right. It's like watching fireworks ignite simultaneously on opposite sides of a stadium, their sparks choreographed by unseen hands. Then there's the quantum entanglement angle. On a subatomic scale, particles can become entangled, their fates intertwined no matter how far apart they're separated. Could this phenomenon, somehow scaled up to cosmic proportions, be synchronizing these gamma-ray sources? Most physicists dismiss the idea quantum effects aren't supposed to work on such macroscopic scales, but the Leo cluster has a habit of bending rules we thought were unbreakable. Or consider exotic particle decays, hypothetical relics from the early universe like actions or sterile neutrinos might decay in ways that produce gamma rays. If these particles were once uniformly distributed, their synchronized decay could create matching bursts across the cluster, like breadcrumbs left by the Big Bang itself. Yet every explanation hits a snag. Annihilation would require dark matter densities far higher than observed. Quantum entanglement at this scale defies known physics. And exotic particles remain purely theoretical. The truth might be stranger still. These ghostly pairs could be our first glimpse of a deeper cosmic symmetry, a hidden layer of the universe where distant events aren't so distant after all. Until we solve their riddle, these mirrored flares will keep haunting the Leo cluster, a silent conversation written in the universe's most violent light. Nestled in the outskirts of the Leo cluster, there's a galactic runt that's rewriting the rules of cosmic evolution. Meet the paradoxical dwarf galaxy, a speck of starlight no larger than a tenth of the Milky Way, yet glowing with the chemical richness of a cosmic elder. This isn't just a small galaxy, it's a time capsule, its stars shimmering with heavy elements like iron and gold at levels that make no sense for its size. In the universe's hierarchy, dwarfs like this should be poor and primitive, the backwater towns of the cosmos. But this one, it's a gleaming metropolis in a body that has no right to be so advanced. The mystery lies in metallicity, the astronomical term for elements heavier than hydrogen and helium. These metals are forged in stellar furnaces, scattered across space by supernova, and recycled into new generations of stars. Larger galaxies, with their bustling stellar nurseries and violent deaths, accumulate metals over time. Dwarfs, with their modest star-forming budgets, usually lag behind. Yet here, in this unassuming corner of the Leo cluster, spectroscopic readings reveal metal levels rivaling galaxies 10 times its size. It's like finding a medieval village with skyscrapers and fiber optic cables, a contradiction that defies the universe's usual blueprints. So how did this dwarf get so glamorous? One camp of astronomers argues it's a relic from the universe's chaotic infancy. In the early cosmos, before galaxies grew to today's sprawling sizes, some pockets of gas might have collapsed into dense, metal-rich stars in a single, frenzied burst of formation. If this dwarf somehow avoided mergers or stripping by larger neighbors, it could have preserved its primordial bling like a cosmic hermit hoarding treasure. Supporting this, its stars show near uniform ages, clustering around 12 billion years old, a sign it might have formed most of its stars in one dramatic sprint, then quietly retired. But the skeptics scoff. If this were truly a survivor from the dawn of time, why does it sit so comfortably inside the Leo cluster, a region notorious for shredding fragile dwarfs with its tidal forces? The alternative theory is just as provocative. Perhaps this galaxy is a thief. Simulations suggest it could have siphoned metal-enriched gas from a larger neighbor during a close pass, gorging on borrowed wealth like a celestial pickpocket. Yet no obvious donor galaxy looms nearby, and the stolen gas would have left traces of disturbance in the dwarf's structure, something current telescopes don't detect. Then there's the dark horse hypothesis, that metallicity isn't always tied to size. Some theorists propose that in certain environments, like the high-pressure cauldron of a galaxy cluster, dwarfs might forge metals far more efficiently than we thought. Supernova in these cramped quarters could enrich their surroundings faster, like sparks igniting dry tinder. If true, the paradoxical dwarf might not be an anomaly at all, just the first of a hidden population we've overlooked, rewriting what it means to be small in a universe that favors giants. Whatever the answer, this unassuming galaxy is a thorn in the side of cosmic classification. Is it a pristine relic, a lucky thief, or a sign that our models of galactic growth are missing a crucial chapter? Every new observation tightens the knot, leaving astronomers torn between awe and frustration. And until we crack its code, the paradoxical dwarf will keep gleaming in the shadows, a silent challenge to the story we thought we knew. In the turbulent heart of the Leo cluster, a cosmic powerhouse is tearing up the rulebook on how dead stars behave. This isn't just any neutron star, it's an unstable magnetar, a stellar corpse with a magnetic field so intense it could erase your credit card from halfway across the galaxy. But what truly sets this monster apart isn't its strength, it's its unpredictability. While most magnetars slow their spins with steady precision, like a top winding down on a table, this one stutters, speeds up, and slams the brakes at random. It's as if the universe's most precise timekeeper has been possessed by a mischievous ghost. Neutron stars are nature's most perfect clocks, their rotations so regular you could set your watch by them. When they're born in supernova explosions, their cores collapse into a dense ball of neutrons spinning hundreds of times per second, beaming radiation like cosmic lighthouses. Over millennia, they gradually lose energy, their rotations slowing in a process called spin down. But the Leo cluster's magnetar, its spin down rate fluctuates wildly, sometimes grinding to a near halt before lurching back into motion like a car with a dying transmission. The leading theory points to the star's interior, a cauldron of exotic matter unlike anything in our solar system. Beneath the magnetar's solid crust, protons and neutrons might dissolve into a soup of quarks, their strange interactions generating turbulence that jolts the star's rotation. Imagine a spinning top filled with molasses. If the liquid suddenly crystallized in patches, the top would wobble unpredictably. That's the kind of chaos researchers suspect is unfolding inside this magnetar, where matter exists in states so extreme, even our best particle colliders can't replicate them. Then there's the magnetic nightmare on its surface. Typical magnetars already boast fields 1,000 trillion times stronger than Earth's, but this one's field seems to writhe like a living thing. Recent observations caught it emitting gamma-ray flares during spin-up episodes, a direct violation of textbook physics, which says flares should only occur when the star's rotation slows. One explanation: the field might be tangling itself into knots, storing energy like a twisted rubber band until it snaps, unleashing bursts of radiation that kick the star back into motion. But the most unsettling possibility involves quantum anomalies. Some theories suggest the magnetar's core might harbor strangelets, chunks of strange quark matter that flicker in and out of existence, briefly altering the star's moment of inertia. If true, this wouldn't just explain the erratic spin. It would mean we're glimpsing a form of matter that hasn't existed freely since the first microseconds after the Big Bang. Every hiccup of this magnetar sends shockwaves through astrophysics, challenging our models of stellar interiors, magnetism, and even the fundamental nature of matter itself. While other neutron stars whisper the universe's secrets in tidy equations, this one screams them in riddles, and the Leo cluster is its echoing chamber. Until we decode its violent, unpredictable language, this unstable beast will remain a glaring reminder. Even in death, stars can defy the laws we thought governed them. Tucked away in a quiet corner of the Leo cluster, a single star glows with a secret so profound it threatens to unravel cosmology itself. This is the impossibly old star, a humble speck of light whose estimated age clocks in at a staggering 14.5 billion years. Here's the problem: the universe is only 13.8 billion years old. That's not a rounding error. That's a star apparently existing before time itself began. At first glance, the star seems ordinary, a yellow-hued main sequence star, not unlike our own Sun. But when scientists analyzed its chemical fingerprints, they found something bizarre. The star contains almost no heavy elements, just hydrogen, helium, and trace amounts of lithium. In cosmic terms, that's the equivalent of finding a living dinosaur. Heavy elements like iron and carbon are forged in stellar explosions, so the first stars born in the universe's infancy should be metal-poor. But this star isn't just metal-poor, it's practically pristine, a relic from an era before supernova had a chance to enrich the cosmos. The age estimate comes from a technique called nucleocosmology, essentially cosmic clockwork. By measuring the star's uranium and thorium levels and comparing them to the radioactive decay rates of these elements, scientists can backtrack to its birth date. The result, a number that defies the universe's birth certificate. So is this a miscalculation, or is the universe hiding something monumental? Skeptics argue for measurement errors. Dating ancient stars is notoriously tricky, and the methods rely on assumptions about the early universe's conditions. If those assumptions are even slightly off, the age estimate could be wildly inflated. Others point to peculiar stellar evolution. Maybe this star formed under exotic conditions, slowing its aging process like a cosmic Benjamin Button. But the radical explanation: our timeline of the universe is incomplete. Some theories, like conformal cyclic cosmology, suggest the Big Bang wasn't the beginning but one in a series of cosmic cycles. If true, this star could be a holdover from a previous iteration of reality, an artifact older than the universe as we know it. Others propose dark matter interactions might have altered the star's apparent age, or that time itself flowed differently in the early cosmos, stretching its lifespan beyond our models. Whatever the truth, this star isn't just a celestial oddity, it's a crack in the foundation of cosmology. Every flicker of its light whispers a question we can't yet answer: are we wrong about time itself? Until we solve its riddle, the impossibly old star will keep burning, a silent rebel against the story we thought we knew. The Leo cluster isn't just a collection of cosmic oddities. It's a full-scale rebellion against the frameworks we've built to explain the universe. Every phenomenon we've encountered, from the phantom galaxy's missing dark matter to the eerie synchronicity of distant stars, chips away at the foundations of modern astrophysics. Take dark matter. For decades, we've treated it as a monolithic, passive glue holding galaxies together. but the cluster's anti-correlation zone and the gravity-defying filament suggest something far stranger, that dark matter might clump, repel, or even interact in ways our models never accounted for. It's as if we've been studying water by only observing ice, unaware of the turbulent ocean beneath. Then there's the standard model of particle physics, which struggles to explain anomalies like the ghostly gamma-ray pairs or the unstable magnetar's erratic spin. These aren't just gaps in our knowledge, they're glaring voids where the rules seem to rewrite themselves. The magnetar's behavior, for instance, hints at exotic quark matter or strange elements lurking in its core, substances that defy the neat categories of protons, neutrons, and electrons. Meanwhile, the gamma-ray pair's mirrored timing suggests either a cosmic symmetry we've overlooked or a form of quantum entanglement scaled to astronomical proportions. Either possibility would force physicists back to the drawing board, questioning whether the universe operates on a hidden layer of connectedness we've yet to fathom. Even gravity itself, Einstein's crowning achievement, falters here. The warped Einstein ring's distorted symmetry implies that mass might not curve spacetime as predictably as we thought, while the unbound hypervelocity star's reckless speed hints at gravitational forces we can't yet map. Modified gravity theories like MUND gain traction in the face of these anomalies, but they too stumble when confronted with the cluster's full array of contradictions. It's as if the universe is taunting us with a puzzle where every piece belongs to a different box. Perhaps most humbling is the cluster's sheer refusal to conform to cosmic timelines. The impossibly old star and the paradoxical dwarf galaxy challenge not just how structures form, but when they could have formed. If stars exist older than the universe itself, or if dwarfs achieved stellar sophistication far earlier than models allow, our entire chronology of cosmic evolution collapses. These aren't minor adjustments, they're seismic shifts that could redefine the very narrative of the universe's birth and growth. Collectively, the Leo cluster's mysteries expose the hubris of assuming we're close to a theory of everything. Every anomaly is a breadcrumb leading beyond the edge of our current understanding, pointing toward physics we haven't yet named. Whether it's dark matter with hidden complexities, gravity that plays by different rules in extreme environments, or quantum effects scaling to galactic proportions, one truth emerges: the universe is far weirder, far more inventive than our textbooks dare to suggest. And until we reconcile these contradictions, the Leo cluster will remain both a crucible for discovery and a mirror reflecting just how much we have left to learn. The mysteries of the Leo cluster aren't destined to remain unsolved forever, because the next generation of cosmic detectives is already gearing up to investigate. Leading the charge is the James Webb Space Telescope, or JWST, an infrared powerhouse capable of peering through dust clouds that once hid the cluster's secrets. Imagine trying to read a book through fog, and suddenly someone hands you night vision goggles. That's JWST advantage, its ability to capture the faintest heat signatures from the universe's earliest epochs, potentially revealing the origins of the phantom galaxy's missing dark matter or the paradoxical dwarf's unexplained metallicity. But it's not just about seeing farther, it's about seeing differently. JWST spectroscopic tools can dissect the chemical makeup of stars in the impossibly old star's neighborhood, searching for isotopes that might settle the debate over its true age once and for all. Then there's LISA, the Laser Interferometer Space Antenna, a mission that will listen for the universe's quietest whispers, gravitational waves. While ground-based detectors like LIGO have caught the crashes of black holes and neutron stars, LISA space-based sensors will tune into lower frequencies, the kind produced by supermassive black holes spiraling toward collision, like the flickering duo in the Leo cluster. If those erratic black holes are indeed dancing toward a merger, LISA could capture the buildup of their gravitational ripples years in advance, offering a front-row seat to the chaos unfolding in the cluster's heart. But the future of cosmic discovery isn't just in the hands of billion-dollar observatories. projects like Zooniverse and NASA, citizen science initiatives, let anyone with a laptop join the hunt. Picture this: while scrolling through telescope images flagged by algorithms, you might spot a new instance of the ghostly gamma-ray pairs blinking in sync, or help map the gravity-defying filament's invisible contours by tracing the distorted paths of distant galaxies. These platforms have already led to breakthroughs. Amateurs have discovered pulsars, classified galaxies, and even uncovered anomalies that professional astronomers missed. The Leo cluster's enigmas could be cracked by someone sitting at their kitchen table, armed with nothing but curiosity and an internet connection. The Vera Rubin Observatory, set to begin its legacy survey of space and time in the coming years, will add another layer to this detective work. By scanning the entire southern sky every few nights, it'll catch the fleeting flashes of the Impossible Supernova's relatives or track the unbound hypervelocity star's path backward to its mysterious launch point. And let's not forget the Square Kilometre Array, a radio telescope network so sensitive it could finally decode the twin radio ghosts' erratic signals, distinguishing between magnata hiccups and something entirely new. What ties these missions together is their potential to turn anomalies into answers. The Leo cluster's contradictions, the galaxies that spin in sync, the quasars that flicker like faulty streetlights, the dark matter that vanishes where it should pool, aren't just puzzles. They're pressure points testing the limits of our knowledge. With every new lens trained on these mysteries, we're not just exploring a distant cluster, we're rewriting the playbook of the cosmos itself. And the most thrilling part, the next breakthrough could come from a telescope's data stream or from your own screen. The universe's secrets are waiting, and the tools to uncover them have never been more within reach. From vanishing quasars to galaxies spinning in uncanny sync, the Leo cluster has ripped open the rulebook of cosmology and tossed it into the void. Each anomaly we've explored, the phantom galaxy with no dark matter, the hypervelocity star flung by unseen forces, the gamma-ray bursts whispering in unison across millions of light years, isn't just a cosmic oddity. It's a crack in the foundation of what we thought we knew. These aren't gaps in our understanding, they're chasms revealing how much of the universe still operates in shadows we can't yet illuminate. Consider the staggering implications. If dark matter can vanish from entire galaxies or warp light in filaments denser than logic allows, then our models of the cosmos are like maps with continents missing. If stars older than time itself burn quietly in the cluster's corners, then the timeline of cosmic history might need rewriting from the first chapter. And if black holes flicker like faulty streetlights, if quasars stutter like glitching holograms, then even the most violent forces in the universe obey rhythms we've yet to decode. Yet there's beauty in this collective ignorance. For all our telescopes and supercomputers, the Leo cluster humbles us. It reminds us that science isn't a ladder climbing toward absolute truth, but a flashlight sweeping through an endless cave, revealing wonders and dead ends in equal measure. Every mystery here, the orphaned star clusters, the warped rings of light, the magnetic monsters spinning erratically, is an invitation, a challenge, a dare to look deeper. And that's the thrill of it all. Humanity's quest to understand the cosmos has always been driven by these moments of bewildering discovery, where the universe shrugs and says, "Think again." The Leo cluster isn't just a destination. It's a crossroads where known physics meets whatever lies beyond. With next-generation tools like the James Webb Telescope and gravitational wave detectors sharpening our vision, we're on the verge of peeling back another layer. So stay curious, because the greatest lesson the Leo cluster teaches isn't about dark matter or black holes, it's about possibility. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And the next revelation, the next paradigm-shattering anomaly, might be hiding in plain sight, waiting for the right moment to whisper its secrets. What will we discover next? The only certainty is this: the cosmos has more surprises up its